Hello again. This is Space Nuts. It's a Q&A edition. This is where we take questions from the audience, throw them in the bin, and discuss other things amongst ourselves. No, we do answer questions from the audience, and we've got a bunch. We've got a question about the naming of the increase in the expansion of the universe rate. Although last episode, if you were listening, that might not be happening, but we will still try and tackle it. There's a question about space elevators. We've got a question about an object that has been getting a lot of attention, TOI 6894b, and a very different kind of question, I will say, regarding Gale crater. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
He's back again for more. Here's Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Good afternoon. How are you going?
I'm well. I'm very well. We've got a lot of questions, and this very first one, we'll jump straight in, comes from Rusty in Donnybrook in Western Australia.
Jonti and Andrew, g'day. It's Rusty in Donnybrook, and I'm wondering what the term for an increase in the acceleration rate for the expansion of the universe is. We've known about, we've had this concept for quite a few years now, and recently we're now looking at a reduction in the acceleration of the expansion rate of the universe as well. So there's a positive and a negative aspect to this. And since we've had all this time, someone may have come up with a better term than jolt or jerk, which seem to apply to very short-term changes and not very gradual changes that we theorize in the expansion of the universe. Thank you.
Thanks, Rusty. Always good to hear from you. He's always got a curveball type question, has Rusty, although we might have been able to curve the ball back to him because last episode we were talking about this very subject, the increasing rate of the expansion of the universe, and he wants to know what it should be called. But the expansion of the universe theory might be tipped on its head because of the research we were talking about last time. So if you haven't listened to the previous episode, 573, go back and have a listen to the last story because it's suggesting that things may not be as they seem, Jonti.
Absolutely. And it's, this advert brought to you by the developing nature of science, essentially. It is how science evolves. We get new observations and we revisit our theories. It's a really good question. And it's a really good point. I have never actually heard any nickname or any kind of easy roll off the tongue phrase to talk about the accelerating expansion of the universe. Cosmologists talk about things in the context of the lambda CDM model. I don't really understand what that is because I'm not a cosmologist, but that is not an easy roll off the tongue nickname. Now, if you go back to the very, 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 very early youth of the universe, there was a period where there was this incredibly accelerated expansion that is hypothesized called inflation. And that was very, very, very early on. That's called the inflationary period. That's a little bit different. What Rusty's talking about here is the evidence which won the Nobel Prize in 1998, I think, for the fact that the universe may be expanding at an accelerating rate. So in other words, the expansion is getting quicker rather than slowing down. And if gravity was winning, you'd expect the expansion to slow down over time as gravity pulls back on the expansion. So this was the great evidence for the existence of dark energy, which people hypothesize contributes something like 68% of all that there is in the universe. It's basically we're a dark energy universe with a fair chunk of dark matter and a tiny little bit of normal matter on the side, like less than 2%. That, as we talked about in the previous episode, may be a paradigm that is about to change. There's growing evidence that the universe is perhaps a bit more complex than that. But in terms of Rusty's question, I have never come across a simple term or nickname or something like that for this theory. People just talk about the accelerating expansion rate of the universe. So unfortunately, Rusty, I can't help you there. To the best of my knowledge, there is no really snappy roll off your tongue thing. I think the model that tries to explain it, like say, is the lambda CDM model, but that is not a snappy public article, BBC documentary type name that will capture people's imaginations. That's just a working terminology in the industry kind of thing.
Yeah. Well, while you've been talking, I asked ChatGPT what we should call it. It came up with a whole bunch. Accelerating universe hypothesis, cosmic expansion theory, inflation continuum theory, dark energy paradigm. You used that word. That's a more scientific style, but it came up with some conceptual names. The Great Unbinding, external expansion hypothesis, runaway cosmos model, the horizon drift theory. I like that one. Metric unfolding principle, the lambda drive, and the everflight theory. That's what ChatGPT's come up with. It's probably just found stuff that people have published.
And I think a lot of those are things that are linked to this, but are other hypotheses and stuff like that.
Yeah.
I mean, I have to admit that I didn't really want to Google things there because I wasn't all that keen on seeing the Google autocorrect coming back saying, "Did you mean expanding waistline?"
It does come up with some really... What I hate is when I know exactly what I'm searching for, I put it in, I've spelled it right, and it does an autocorrect and finds me something else.
Yeah.
That's not what I asked for. I told you to look for, lemonade, not lemons.
Yeah.
Anyway, thanks, Rusty. Maybe you've got a name you can send through to us, or maybe somebody could pose the question on the Facebook group or the podcast group on Facebook and come up with some names. I'd be interested to see what you think of. Our next question comes from Barry. Barry said, I recently read a sci-fi book called First Ascent based on a space elevator. The elevator had 6 stations, one being Earth, 2 at 300 kilometres, 5 at 6,200 kilometres, and 6 being geostationary orbit at 35,786 kilometres. I know the International Space Station's about 400 kilometres, and the crew are in free fall. This is due to the forward motion of the ISS, which is constantly falling and is in orbit. In the book, they discuss that at Station 1 at 300 kilometres, the travellers are still at about 1G. Station 5 at 6,200 kilometres, they're at 1/4 G. They're on the moon, they'd be at 1/6. And free fall weightless is at Station 6, 35,000 and a bit kilometres. Can you discuss with accuracy of feeling gravity if and when a space elevator is built? Of course, this is totally hypothetical for at least the next few hundred or 1,000 years. Yes, it is. It's not something we can do yet. And even if we could, I don't know if it would be the logical way to do things, but we don't know what reasons in the future we might need one. So we'll just leave it hanging in the air. Boom, boom. So can you discuss the accuracy of feeling gravity if and when a space elevator is built?
Yeah, it's a fabulous question. And it does sound like this book is hard sci-fi in the sense that it's based on real-world physics, is what I'd say. It sounds like the numbers are right to me. Now, the argument is that a space elevator, once you can get it built, it's an incredibly challenging thing to do, beyond us at the minute. But once you've got it, suddenly it makes it much easier to access space. And part of the argument there is that we will be extracting resources off Earth, and so it's likely that there'll be more stuff coming down the elevator than going up. So effectively, you can ride up for free, just, as a side effect of it. So it's one of those things that has become a staple of kind of relatively near-futurish science fiction. The numbers here about the acceleration that you'd feel are accurate. So there's 2 ways that you can get gravity if you're on a space elevator. One is that you would feel a pseudo-gravity based on the acceleration of the lift going upwards. And you get this when your lift goes up or when it falls. If you're in a building that has one of those ultra-fast lifts, you feel a little bit more weightless if it's going down. You feel a little bit heavier when it's pulling up initially, because the floor will be accelerating up to meet you or accelerating down away from you. And that will mean that you will get a change to the gravity you would otherwise feel if you were stationary at that altitude. So some sci-fi books I've seen with kind of far future type technology have your space elevator able to accelerate at or in excess of 1G, very hard acceleration. And what they do is they accelerate slowly going up through the atmosphere and then speed up once you're in vacuum, with the acceleration offsetting the drop in gravity you get as you get higher, keeping you at a comfortable level of gravity. And then when you're halfway to the end point, it turns round. You have a brief period of pseudo-weightlessness, and then you accelerate in the other direction to slow down. So that's one way that you could get kind of constant gravity throughout almost the entire trip, and that will get you to your endpoint pretty quickly. So if you're accelerating at 1G, you actually accelerate very quickly, and that's why you wait till you're out of the atmosphere to do that. But the other thing is that as you ride up on a space elevator, the higher you get, you will still feel gravity pulling you down through the soles of your feet, but the strength of the gravitational pull you feel will weaken. Now, when you're at the endpoint, which is a space station in geostationary orbit, you are moving around the Earth at orbital velocity, and the space station around you is moving around the Earth at orbital velocity. So that's why you'd be weightless, because you're accelerating at exactly the same rate as your surroundings. So compared to you, there is no acceleration pulling you down because the floor's falling away at exactly the speed that you're falling down, effectively. So that's what you'd experience very briefly if you were in an elevator on Earth and the wires were cut. When you started to fall, you'd be weightless, but you wouldn't be enjoying the experience.
No, not
You'd
much.
be worrying about what happens at the bottom. Although, thanks to a very, very silly TV series that's quite swearing and offensive called Archer, my understanding is that lifts have been designed in such a way that if the cables break, there are safety mechanisms in so you won't just splat at the bottom. There was a whole episode based where they were stuck in the lift and they were worried about that. It's bizarre what you learn from random TV cartoons. Anyway, so you have at the upper limit effectively 0G. You are weightless. You are experiencing the Earth's gravity, but so is the space station around you and you're falling together. Just like mentioned with the International Space Station. At that point, if you had some way of sitting stationary in space, so in other words, you were not orbiting the Earth, you were motionless, but you had a rocket holding you up, you would still feel the Earth's gravity pulling you down because the rocket would be pushing up against your feet, essentially. Right. And you'd feel the strength of gravity there. You're at 36,000 kilometers, which means you're 42,000 kilometers from the center of the Earth, which means you're 7 times further from the middle of the Earth than we are here. The strength of gravity falls off as 1 over distance squared, so you'd feel about 1/50th of a G there. So if you were able to sit still rather than falling with the space station, you would feel a little bit of gravity there, but it wouldn't be that intense. At the lower altitudes, the effect is dominated not by your rotation movement because you're going much slower than orbital speed, but by the fact that gravity is pulling you down, but the lift is being winched upwards. So if you lifted your space elevator up and you stopped at one of these stops, and that's why they talk about the stops, I suspect. If you stopped at 300 kilometers at a station just above the atmosphere, attached to the tether, moving around at the same speed the Earth's rotating underneath you, you'd feel an acceleration due to gravity that is a little bit smaller than that we feel at the surface of the Earth. Now, if you're at the top of Mount Everest, technically you feel a slightly lower acceleration due to gravity than you do at the sea level, because you're further from the center of the Earth, so that 1 over r squared component in the acceleration due to gravity equation is a slightly bigger number on the r squared, which means your acceleration due to gravity is a slightly smaller number. But that's imperceptible to humans, but we can measure it with instrumentation. That, incidentally, is why if you really wanted to lose weight, but you're being lazy, if you want to get weighed in the place where you will weigh the least on the Earth, you go to the top of that mountain near the equator. Is it Anaconda, I think it is? Which is a point on the Earth that is furthest from the Earth's core, because you've got the bulge of the Earth's equator on top of the height of the mountain, and you will feel a slightly smaller acceleration due to gravity there because you're further from the Earth's core. So at 300 kilometers up, you've only changed your distance from the center of the Earth by about 5%. And so you've probably changed the acceleration due to gravity by less than 10%. It's probably enough that you'd be able to notice it. Walking around would feel slightly unusual, but it wouldn't be a problem. The station number 5 that is mentioned here at 6,200 kilometers, that means you're nearly twice as far away from the center of the Earth now as we are on the surface of the Earth. Surface of the Earth, we're about 6,380 kilometers from the middle. Varies a little depending on your altitude above sea level and where you are on the globe.
Yeah.
Add another 6,200 kilometers, you've effectively doubled the distance, which means 1 upon r squared is 1 over 2 times 1 over 2 is 1 over 4. So the acceleration is 1/4 of a G. So we've dropped the strength of gravity you'd feel by a factor of 4. And at that point, that is hugely noticeable. It's a little bit stronger gravity than you'd have on the moon, but not by much. Now, I guess this is the kind of thing where you could, if you were sending people to Mars and you wanted them to experience Martian gravity and see if they could cope with it, you had a training and a testing program, and anybody that got too travel sick or whatever and couldn't adapt was bumped out of the program. What you do is you take this space elevator, you figure out exactly at what height above the ground you would emulate Martian gravity perfectly, and you build a training station there. Because at the end of the day, if you've got a space elevator, you may as well put an extra level on it. And that way you can train people up for Mars. And I could almost imagine a future where they have one for the moon as well,
Yep.
Go up there, spend a few weeks training in lunar gravity and see if you can hack it on the surface of the moon. And anybody who can't, no shame. We all have slightly different balance systems and all the rest of it. If you can't adjust, that's fine. You can work on Earth, no problem. But so it does sound like the science in this book is robust. In other words, it's hard sci-fi. It's based on our current understanding of physics, and that's how it would work on the space elevator. So hopefully that makes sense, and it is a really good example of how you can use a science fiction book to teach people science fact.
Yeah, absolutely. Yeah. Thanks, Barry. Just a side question, Jonti. Do you think we ever will build such a thing?
I'd be a fool to say no on it. I really hope that we do. And given the impact we've seen, both good and bad, from the advent of reusable spacecraft and the growth of commercial space, that's dropped the cost of launching a kilogram of material to space by between a factor of 10 and a factor of 100. And it's been revolutionary. If you could drop that cost to essentially nothing, what that enables is an enormous expansion in our use of space. It also enables the kind of space tourism type stuff. Because if you have a docking station at geostationary orbit, you've already done a hell of a lot of the work of getting out of Earth's gravity. So it's much easier to launch to Mars or the moon, or pick your tourist destination. From there, pick your research destination. You hugely reduce the cost of doing both research, commerce, tourism by getting people up to that altitude. You don't have to get through the atmosphere, but you also don't have to burn your rocket to get up through that hardest, steepest part of Earth's gravity well. So once it is technologically feasible, I suspect what you'll have is it'll become technologically feasible, then not too long after that, it'll become commercially feasible, and that's the point people will look at doing it. And the big caveat there would be, is it actually ever going to be technologically feasible? But it's near enough future science that people have already had suggestions about the kind of materials you could use to make the cable, because that's the big constraint, is actually making the cable. Wouldn't need to be a lot stronger than spider silk, for example.
Yeah.
But it is not so far beyond what we can make now that people think it's impossible. Rather, people think it could be feasible, but we don't know how yet. And in that kind of context, we're incredibly good at doing the impossible and the improbable as a species. So long as we don't wipe each other out, so long as the shutdown eventually ends, then perhaps we'll be able to figure this out. And, probably not in our lifetime, but may well not be as far beyond that as you'd think.
Well, if you go back 200 years and tell people, hey, where I come from, we've been to the moon, they'd think you're a witch. I mean, they just wouldn't believe it. So who knows what's possible in 200 years' time.
Yeah, the thing that makes my head hurt with that is we're almost at the point, in fact, I think we possibly are at the point now, where it is longer since the first moonwalk than that moonwalk was from the first powered flight.
I know. Isn't it amazing? It's incredible how far we've come in such a short period of time. Thank you, Barry. Great question. Our next question coming up in a moment on Space Nuts. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally, of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts. And don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space Nuts.
And you're with Andrew Dunkley and Jonti Horner. This one comes from Casey in Colorado. I was hoping that you could please explain why TOI 6894b is such a big deal and what it means for our understanding of the universe. Love the show, and I hope you're both well. Thanks. Thank you, Casey. Yeah, so I did a bit of research on this particular planet, TOI 6894. It's a massive, massive gas giant. But what makes it unusual is that its star is a bit of a mouse. So they're trying to figure out how such a massive planet can exist next to such a tiny star. I think that's the guts of it, isn't it?
It is. And it's a really good example, again, of the detective story side of astronomy. The way that we can't really do experiments, so we have to learn through observation. And so the interplay is not experiment and theory like it is in other disciplines, but it's observation and theory. And that leads to our science being different in subtle ways, even down to the structure of how we write and how we communicate. It's less about testing hypotheses than other disciplines. There's a lot of complexity in that. Now, if you go back to when I was a kid and I was learning all about astronomy, we didn't know of any planet around any other star. And we thought we had a very good feeling of how the solar system formed and therefore, by extension, what kind of planets we would find.
Yeah.
And we expected that you'd find giant planets like Jupiter out beyond the snow line, several astronomical units from their star going around on orbits that are measured in decades, and rocky planets in the interior. And that's how planetary systems would form, and the solar system would be typical. We then found 51 Pegasi b, which is a planet comparable to Jupiter going around its star every 4 days, and that kind of threw everything out, and we had to improve our theories. Now, what it led to was a refinement of the theories of planets forming in disks rather than them being totally chucked out on something new. But that first discovery of a planet around a sun-like star really set the scene for the fact that the diversity of planets we find around other stars is overwhelmingly greater than we could have ever imagined. Planets are ubiquitous. Every star has them. That's what we've learned. But the variety of planets is much greater than we could have imagined. And all of that data has been a fabulous resource for scientists trying to understand the process of planet formation and the variety of ways that that process can proceed. Effectively, every planetary system will be unique in the same way every human's unique. They're the product of the environment that they're forming. The mass of the disk is important, the mass of the star, but also the cluster environment they're forming. There's a lot of things going on that mean if you have two identical stars with two identical disks, you'll still get different planetary systems at the end. So we're learning more about planet formation, and it's the outliers and the oddities that really drive that science forward. Which brings us to TOI 6894. What we found typically is that giant planets are common in the cosmos. We find them easier than everything else because they're more obvious. So our discovery techniques are biased towards finding planets the size of Jupiter and Saturn and against finding planets the size of the Earth. That's why we find a lot more of them. And what the results have shown is that giant planets, massive planets like Jupiter and Saturn, are more common the more massive the star is. They're also more common the higher the metallicity of the star is, so the higher the amount of solid material would have been around that star. And typically, we don't find giant planets like Jupiter and Saturn around the lowest mass stars. And the argument has always been that low mass stars form from low mass disks, where there's just not simply enough for planets to form there. Then you get TOI 6894b. So the star TOI 6894 is a little red dwarf. It's only about 20% the mass of the sun, about 238 light years away. The planet going around it is a little bit bigger than Saturn, but about half the mass of our giant planet. So it's another one of these super puff planets that we've talked about before. It's heavily irradiated, has been inflated, and that probably suggests that it's migrated in the recent past. Now, people who've looked at data from Kepler and TESS more recently, which looked at so many stars, have been able to do a kind of statistical study. And what they've found is that for red dwarfs, like TOI 6894, only about 1.5% of all red dwarfs harbour any giant planets. And TOI 6894 is the least massive star to be found with an orbiting giant planet around it. So that's why it's really, really interesting. Now, there's a number of different processes that go on in planet formation and star formation. And we've talked before about the blurred lines between planets and brown dwarfs and stars. And back in the day, we thought we had a very clear rational explanation that they're formed in different ways. But now we see brown dwarfs being discovered free-floating that are lower mass than the canonical traditional 13 Jupiter mass limit. Anything smaller than 13 Jupiter mass used to be thought of as a planet. Similarly, we're finding things that they're calling planets that are more than 13 Jupiter masses, so the lines are getting blurred.
Yeah.
And I think we may see a bit of a paradigm shift in years and decades to come, where part of what defines whether you're a planet or a brown dwarf at the top end is actually how you formed, and by extension, what's buried deep in your core. So a planet like Jupiter has a massive 20, 30 Earth mass solid core at the middle because it formed from a process of core accretion. You get solid material agglomerating, forming bigger and bigger bits until you form things kilometers across, then thousands of kilometers across, objects like the Earth, and the more they eat, the bigger they get. Eventually, you get to 20 or 30 times the mass of the Earth, 10 or 12 times the mass of the Earth to start the process. When you're at that point, your gravity is strong enough to start capturing hydrogen and helium gas from the nebula that previously would have escaped. You finally can hold on to it. And because there's more of hydrogen and helium than everything else combined by a couple of orders of magnitude, 98% of everything is hydrogen or helium. Suddenly you've got this enormous new untapped food source. You can quickly devour all there is, and your mass grows really rapidly until you open a gap in the disk, and voila, you've got a giant planet in a gap. And we talked about this a bit last week. That's core accretion that leads to giant planets that are planets with a solid core and a thick atmosphere, and that atmosphere can be the bulk of their mass. You've then got a method called gravitational instability, where your disk is sufficiently massive compared to the star in the middle that it can become unstable itself, and you can get it essentially globbing together to form massive objects on a very short time scale. And that's probably, to be honest, the process by which binary stars form, where you get a second star forming on a quite wide elongated orbit, whatever. And I've always had a suspicion, back when earlier in my career I was at the University of Bern, and this is 20 years ago now, there was this kind of conflict for giant planets where people said, one of these two methods will be right and the other one will be wrong. And you've got core accretion or gravitational instability, and it was a big kind of which one of them is right. And I've always had the feeling that in the right conditions, both of them can happen. And this suspicion that brown dwarfs and stellar companions probably form through this gravitational instability process, which leads to more instability and kind of lowers the likelihood of planets then forming in the system. And you'd form an object there that doesn't have that massive core in the center. It's basically the composition will match the composition of the material in the universe. This is a really interesting one because this planet is so massive compared to its star. This is kind of equivalent to the sun having a 5 or 10 Jupiter mass planet, probably. Something like that, because a more massive star would have more mass, and you wouldn't just 5 times the mass of the star is 5 times the mass of the planet. It would go a bit more than that. So it's a real surprise, and there's a lot of investigation to be done to try and figure out what the formation process of this object is. The fact it's a super puff, it's puffed up, it's bigger than Saturn but less massive than Saturn, suggests that either it's very close into the star and it's getting hugely irradiated. If that's the case and it's been losing mass, it was probably more massive in the past, which adds further weight to maybe this was a bigger thing in the past and maybe it could have been a very low mass brown dwarf rather than a very high mass planet. Or maybe it's telling us that you can get M dwarfs, red dwarfs, which have a disk massive enough to form giant planets on occasion in the right setup. And we just need to learn more. But it seems very unlikely that if the properties of the disk around this star were similar to the bulk of disks we found, there should not have been enough solid material to get the core accretion process to go quickly enough for you to get a giant planet, never mind one close enough in like this one to then become a bit of a super puff. So there's a lot to learn. It's very close to its star. It's only 3.9 million kilometers out from the star. So it's much more comparable to the Jovian moons. If you imagine the star being where Jupiter is, this is comparable to some of the moons of Jupiter in distance. And that's another of the reasons it's just really hard to imagine how it could have formed so close in. there's a lot to dig into in this. They're looking at the chemistry of the atmosphere because this planet's close enough in to be hot enough that we can actually get light from it and we can look at its atmosphere. Seems to be kind of methane dominated, I think, which is really, really odd. There's all sorts of weird stuff going on. But because red dwarf stars are so common, even though giant planets like this are rare per red dwarf, there's probably a hell of a lot of them out there. You know, red dwarfs are the most common star in the galaxy by far. You know, some estimates are, you know, up to 3/4 of all stars in our galaxy will count as red dwarfs, which means you could have 100, 200, 300 billion of them out there. So even if only 1% of those stars have a giant planet like this, you know, 1% of, you know, 100 billion stars is still a billion stars.
Yes.
Now, maybe this planet is both rare and common at the same time.
Yeah, that sounds like a very good theory, actually.
Yes.
Casey, thanks for the question. If you'd like to read up on it, you can go to sci.news, the website, because they've got a great article on it, but they've also published a recent paper in the journal Nature Astronomy.
3, 2, 1.
Space nuts.
Our final question. Jonti, I don't know how to introduce this, so I'm just going to let it speak for itself.
Hello, Space Nuts. This is Philip McCrackpipe, future Nobel Prize winner here again. This time, I've got my bonny lassie, the famous English soprano, Anita Fix, here with me. That's Anita Fix, F-I-C-K-S, thank you. Not F-I-X. So many people get that wrong. I have this question about Gale crater on Mars and what kind of life it might have supported. Being a famous soprano, I'd like to sing it to you. Oh, pardon my voice today. I have a slight touch of the anthrax. How many lovely life forms might have grown in an ancient Martian crater? Could they have thrived or only just survived in an ancient Martian crater? Were they all just single soul, or did they fly like Tinkerbell and laugh and sing and play in microscopic trees? How many lovely life forms may have grown in an ancient Martian crater? Did they breathe the atmosphere? Were the predators to fear? Elucidate your views ecosystematically. Thank you, lovely space nuts, for listening to this tripe about an ancient Martian crater.
I hope you get over the anthrax real soon. Thanks, Anita. I think I need...
We're a very different kind of musical ensemble, if I remember rightly.
Yes, I think I need a fix. Bottom line, was there or could there still be life in Gale Crater, and what would it be like?
Lots of places to go with this. I mean, two immediate diversions just spring to mind listening to that. It's lovely to get a musical entry from such a storied soprano, but reminds me, probably my favourite group are a Finnish symphonic metal group called Nightwish. And this is relevant, I promise. Symphonic metal is this weird fusion of metal and opera. So you could describe it as operatic metal. And the lead singer is a very storied classical soprano called Flo Jansen, who's just ridiculously awesome in many, many ways. Reason it's relevant is we were talking earlier on about Eugene Shoemaker in the previous episode, about Ashes going to the moon, things like this. Nightwish on their most recent, album before last, had a track called Shoemaker, which was a eulogy, a tribute to Eugene Shoemaker, which has a lot of rocky stuff at the start, but from about 3 minutes 50 onwards has a very, very operatic, classical Latin funereal mass, which is utterly astonishing. So I do recommend people, I don't know if we can play it on the podcast. I don't know if we can play out because I don't know how rights issues work.
There are rights issues, which precludes us, I'm afraid.
Yeah.
I did listen to what you sent me. You sent me a link on YouTube, so we could probably send people there. But
it's a bit of a musical tour de force because it's got bits from William Shakespeare in there, which is the epitaph on Schumacher's tomb. That's why you've got the bit of Shakespeare spoken word in there. It's unusual, but it's incredibly touching. Anyway, so love a bit of musical science. The other thing that occurs, without casting any aspersions on Anita there, is the ability to sing while staying in character, which is good. And it reminds me of another thing. I listened to, and I've listened to multiple times now, the phenomenon that is Dungeon Crawler Carl. And at the end of the first audiobook, I was a bit put aback because there wasn't a cast list. And I thought, hang on, this is a bit dodged. There's multiple people involved with this who are not getting credit. There's just this one guy getting credit for doing all the voice work and all the rest of it. And it really is just one guy. And it's remarkable how certain performers can voice multiple different characters to a degree of distinction that you assume that there's multiple people involved in the voicing. So, incredible ability to sing well in character and stuff like that. So huge credit on that. In terms of the question and questions, it's all about life on Mars. Now, we know that Mars in its youth was both warm and wet. It was an ocean planet, that's fairly well established. And the transition from warm, wet Mars to cool, dry Mars would have been very slow and gradual. So any life that did get going will have had time to adapt and move potentially. That's a big part of the focus of the search for life on Mars, both looking for evidence of past life, and that's part of what the rovers are doing, driving around in Gale and Jezero Crater, or Jezero Crater, I think it's pronounced. It's also why we're interested, for example, in the lakes of permanent liquid water at Mars' South Pole. But we don't know for a fact that there was life on Mars. It still was there, wasn't there? We're trying to find out. The idea, though, is that when Mars was young, it was warm and wet. It had oceans. There may have been icy, slushy oceans, more like what you get in the Arctic than what you get near the equator. We don't fully know on that yet. But there was a vast expanse of liquid water on Mars' surface for an incredibly long, protracted period. All the conditions that on Earth would lead to life establishing and thriving. So there's a very real possibility that Gale Crater, this ancient Martian crater, was teeming with life in the past. It is, I think, so the challenge here is that we've only got one example of life in the universe to go off, which is life on the Earth. So we tend to form all our assumptions about the pathway that life will follow and how it will develop based on that example. Now, just with the last question, we were talking about our ideas on the formation of planets when we only had one planetary system to go on, and how wrong they were when we found the second planetary system around a sun-like star.
Yeah.
So the caveat to everything I'm about to say is that currently we know of one place with life and one planet with life. So I'm basing it off assumptions based on how things developed on Earth. And on Earth, we had simple life from about 3,500 million years ago. The evidence for the oldest fossils on Earth that are widely accepted is about 3.5 billion years ago, found in the Pilbara region in Western Australia. There are some fossils that are arguably older, but they're still controversial. For the first 3 billion years of life on Earth, all you had was single-celled life. You had an incredible diversity and variety of simple life, but that's all you had. It's only about 500 million years ago, give or take, that you started to get complex life. So the argument following that would be, if Mars had life, and if that life followed a similar pathway to the Earth, then you would expect that that ancient life would all have been simple life. Now, the other thing that argues for that is if you look around on the Earth today, we've got life in abundance all over the place. But the more complex the life is, the more limited the variety of environments that it can exist in, if that makes sense.
Yeah.
So, obviously, simple life can exist in a wider variety of conditions and will exist earlier than complex life. And so the argument then would be, with all those assumptions, and I know I'm doing a lot of cover your own ass here, but with the assumption that everything followed the way that things went on Earth, my expectation would have been that Gale Crater could well have been teeming with life, but it would have been simple life. It would have been single-celled life. Now, single-celled life still lives a very vibrant and diverse set of lives, so there will be things interfering with each other and eating each other and all that kind of happy stuff going on. But it's likely that there weren't giant sharks or octosharks or whatever, swimming around in the ocean in Gale Crater. And I suspect that if there had have been, we'd already possibly be finding evidence in the form of fossils. I may be wrong on that, but I suspect that the fact we haven't yet got definitive proof of ancient life on Mars suggests that the life that was there, if it was there, was simple life and single-celled life rather than complex stuff. But I stand to be corrected on that. I look forward to the confirmation of the discovery of ancient fossils on Mars if we ever get there. Confirmation of life elsewhere will be awesome. So it might be worth getting Anita back on the show in a decade or so to sing the sequel is, now that we know there was life there, what was it like?
Yeah. I think we will find something somewhere, probably Mars, but maybe on some of the ice moons further out. But there's got to be something. I think it'll be microbial, as you said, but it's just, you look how life just grabs on Earth with given minimal opportunity. And I think that same thing exists in the universe elsewhere. Life, if there is just a small opportunity, it will grow. And absolutely. I think that's what we will find. But whether or not we find another so-called intelligent place in the universe or an intelligent species, that's a bigger call and a completely different ball game indeed. Thank you for the question, Anita. And if you would like to listen to the music that Jonti was referring to, you can go to YouTube, do a search for Nightwish Shoemaker, the official lyric video. They've got 1.82 million subscribers. Yeah, it's extraordinary.
It's a style of music that isn't really widely known in Australia. So when I've gone to see them on the odd occasion, they've come over here. We've been down at the Tivoli in Brisbane, which is kind of 1,000 people. When they go anywhere else in the world, they're doing packed stadiums with 100,000 plus. So it's a different genre. They along with a group called Epica and a male-led group called Camelot, are probably the three leading light groups in that genre of symphonic metal, which is at the interface of opera and rock, effectively. But they've had a number of scientifically themed songs over the years. In fact, there's one that I have as recommended reading stroke listening for my undergrad students. That's kind of a 20-odd minute long story of the evolution of the planetary system and life on Earth and all the rest of it. So they've done interesting things.
I'm sure they have.
All right. Shoemaker's a good listen.
Excellent. All right. Thanks to everyone who contributed. If you would like to send a question into the Space Nuts website, just go to spacenutspodcast.com or spacenuts.io and click on the AMA button at the top and send us your text or audio question. Don't forget to tell us who you are and where you're from, and leave your email address so we can spam the hell out of you. No, I'm only kidding, although I think that is part of the deal. We'll see. But yes, and guess what? Hugh in the studio just turned up. Hi, Hugh. Woo-hoo. Bye, Hugh. And thanks to you, Jonti. We'll catch you on the next episode.
It's a pleasure. Looking forward to it.
Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. And we thank him, we thank everybody, and thank you. And from me, Andrew Dunkley, thank you for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.